Today I'm going to continue a problem that I did earlier. So if you have not yet watched part 1 of this video, why don't you go ahead and do that now. What I have done is summarize kind of the conclusions that we came to. If you recall, we went through four different steps, A, B, C, and D, and I asked you to find the pressure, the volume, and the temperature at each of those steps. So here's kind of a summary of those. If you recall, I also made a nice little picture for you which kind of showed what was happening. So this was our starting process, and then what we did is we added some heat to the process, doubled the temperature. We then compressed it and cooled the temperature, and then we expanded our cylinder and kept the temperature constant. So notice again at step A and step D, we ended up exactly where we started at the beginning, and you can see that the numbers bear those out. So what I would like to do, so here's our new questions we have here. So as usual, if you haven't yet done so, go ahead and take a moment, see if you can solve these on your own, and then come back to the video. Alright, so let's go ahead and do this. At this point, we're just going to go ahead and plot our points. Remember, we have pressure on the y-axis and volume on the x-axis. They will often, we'll go ahead and put the units and the kind of the multiplier over here as well, just to save ourselves some time. So yeah, let's just go ahead and plot it. So process A was 1 pressure and 2 volume. So 1 pressure and 2 volume is going to be right here. So let's go ahead and label that as part A. Step B was 2 and 2. It's going to be up here, part B. Okay, we can go ahead and connect this. One thing you do want to do is make sure you draw the arrow. The direction is important. So we're going from A to B. All right, letter C says we're at a pressure of 2. By the way, this is what kind of process? Constant volume. We call that an isochoric process. All right, we're now going to go from to 2 to 1, so 1 volume and 2 pressure isobarically. That means the volume's going to remain constant, so we're going to move this way. And then lastly, we're going to go from C back down to A. Now the way we connect this, we're not going to just simply draw a straight line from here to here. This is an isothermal process. So remember, in an isothermal process, our shape is going to look something like this. Remember, this is like a 1 over y graph. X equals 1 over y, or y equals 1 over x. So the next thing we're going to do is find the amount of work done at each step for each process. So we'll just kind of go through each of them. So the first one would be the work done from A to B. Okay, work done from A to B. Well, notice in this picture we're going from A to B. Remember, to find the work, we're just going to find the area underneath here. You could also write this equation as negative P delta V. That's our equation for work. But it's simply going to be the area underneath. So notice here the volume is the same. So the volume staying the same. This is isochoric. So since there is no change in volume, the amount of work on this process is always going to be 0. All right, and you can see that here if we go back to our picture A to B. Since there's no change in volume, there can be no work done. You need to have some force, some distance, like going to B to C or going from C to D. You need to have a change in volume in order to get work. So let's go ahead and do the next one. We'll go do the work from B to C. The work from B to C is, well, again, we can just kind of use our equation if we want. All right, B to C, we're going from the pressure staying at 2, so it's going to be negative 2, and then our volume is going from 2 to 1, so we would subtract 1 minus 2, okay, and actually I forgot the little multipliers here, right, so that would be times 10 to the 5th, times 10 to the negative 3rd, and actually for future, we just know that's going to be 10 to the 2nd. Okay, so we multiply this. Notice we're going to get 200 joules. And we did get a positive number. Remember, our positive work means that work is being done on the system. And actually, I personally prefer not to kind of try to memorize what's plus, what's minus. just kind of look at the problem and look at what's going on in this situation. So we're going from B to C. Remember, our system is going to be the collection of atoms on the inside. So to go from B to C, our force is this way. So work is being done on the atoms here. Something from the outside, the atmosphere, for example, is pushing it down. Work is being done on the atoms, and therefore there's going to be an increase of energy whenever work is done on something. That's why we have a positive number. Just get in the habit of figuring out, is it on or is it by, and not worry too much about the positive and negative. So let's look at from work from C to A. Oh, by the way, B to C, remember, what we're really doing here is we're finding the area underneath this. Okay, so if I draw this out, this little orange here, we're finding the area underneath this here. And that would be, well, it's simply this rectangle, which we're multiplying the base times the height. And that's what we're doing here as well. All right, so the next one is C to A, right? So C to A. This one's a little bit tricky. And in fact, I'm going to ask you just to do an approximation here. Notice here that this is curved, right? And notice also this says pressure, but the pressure is changing here. So really if you were going to do this correctly, you would have to find the area underneath this curve. And to do it properly, you would have to do some calculus, right? But we are going to kind of keep it simple. We're just going to approximate this as like a triangle here, and this as a rectangle here. And when we find the area of this plus this, okay, that's going to be approximately equal to the total area. So it is an approximation. The number is not going to be exactly right, but it will give us a good ballpark. You could also, another way of doing it is saying, oh, let's just look at the average pressure. What's the average pressure here? And then go from there. So I'll go ahead and do it like that. Actually, we can do the area, it's easy enough. So we'll go 1 and 1, right? So the area of this would just simply be 1. And then the area of this triangle would be 1, what's a triangle? So a half, right? So this would be 0.5. So that would be 1.5 times 10 to the second. And that's going to get 150. Notice you would get the same thing if you use your P average there. Okay, so is this positive, is this negative? Well, notice if I were to do this, I would have to put a negative here. But again, what's more important is looking at, is work being done on or by the system? So if you look at the picture here, this is expanding. So the inside particles are pushing up. They're doing some work, pushing the cylinder up, expanding the cylinder, and therefore work is being done by the system. So the next question asks to find the net work for the whole entire cycle. So hopefully for this, simply you're just going to add it up, all the different processes, A, B, B, C, and then CA. That gets us back to where we started. That would be the whole cycle. And so again, when we do this, 0 plus 200 minus 150, that's going to give us 50 joules. Okay, and again, you want to label this done on the system, by the system. This is done on the system. So notice the net work for this entire process, there was more work done on the system than there was done by the system. So in the end, the net work is going to be done on the system. One last thing I do want you to notice, what we did is we took this orange area here, right? That was B to C. We took this yellow area, that was C to A, and then we ultimately subtracted those two. So in fact, let's get a good color, we'll get red. So in fact, the net work is essentially the area enclosed, okay? The area enclosed by our cycle, and that's going to be our net work on or by the system. To figure out if it's on or by, you just look at, well, what's the dominating factor? What's the one up above? So B to C is the dominating factor, and again, our volume's decreasing, therefore work is being done on the system. So the next question is asking, what is the change in the internal energy of the system? So recall, internal energy, U, is directly proportional to T, proportional to the temperature. If you want to get the exact number, that would be 3/2 N Boltzmann's constant times T, or 3/2 nRT. Or if you actually look at it, nRT is equal to PV, right? So 3/2 PV. But the key idea is that it's proportional to temperature. Well, notice we went from A, B, B, C, C, D, so the change in U, we're back at A. So the temperature at A is the temperature at A, right? So the change in U is actually going to be 0. And this will always be true for a cycle. One misconception I just want to address is U is proportional to temperature. Q is not necessarily proportional to temperature. So in other words, adding heat does not necessarily mean that the temperature is going to increase. In fact, you can look at one of the processes. Let's look at C to A. Okay, in C to A, we are actually removing heat, C to A. Adding heat, C to A, but the temperature is staying the same, right? This is an isothermal process. And if you look at C to A, this expanded, we added heat here to expand this. However, the temperature remained the same. And so again, that's a very common kind of trick question they're going to give you on the AP test. U is proportional to T, Q not necessarily proportional to T. And actually, we'll see this in the very last question. I haven't been numbering these, but this is letter I. In the very last question, it's asking how much heat was added for the entire cycle, or heat removed. Well, we're just going to use our first law of thermodynamics, delta U equals Q plus W. And then for this problem, as we just said, delta U is equal to 0. All right, and so in other words, Q is equal to the opposite of W. And W, as we just said, was 50 joules. Okay, remember that was 50 joules done on the system, which means it had a positive value. So if we now negify that, we're going to get Q equals negative 50 joules. So in other words, heat was removed from the system. And again, going back to what I just said, notice ultimately we took heat away from the system, but the temperature remained the same, right? The temperature stayed the same back when we went to the last step. So this actually has a name when we have something done on the system and removing heat. So let's go and label this. When work is done on the system and heat is removed, this has a name, this device. And actually, you all have these in your house. This is what's called a refrigerator. And in a refrigerator, ultimately work is done on, and obviously you know heat is removed from the inside of your refrigerator. In fact, if you were to look on the back of your refrigerator, you'd see what's called a compressor. Okay, the purpose of the compressor is to have work done on. And then actually, if you go to the back of your refrigerator right now, what you'll notice is that it's hot back there. And that's because the purpose of this is to remove heat from the inside, and it's removing it to the outside. All right. Last little piece, if we go back to this, what would happen if we totally reverse this process? So we went from A to C, C to B, B to A. Notice that the signs here would all be flipped. In other words, in the end, the numbers would be the same, the signs would just be flipped. So in the end, you would have negative 50 joules. So we'll flip the process, flip the direction. Okay, let's use a different color. Flip the direction. If we flip the direction of the processes, notice you're going to have work done by the system, and you're going to have heat added to the system. Actually, the way we usually rephrase this is we'll say we're going to add heat and then have work done by the system. The system's going to do some work. This has a name also. This is what's called a heat engine. Okay, you probably drove to school today in a heat engine. The purpose of that, or how it works, is you add heat, right? You add your gasoline, you light it on fire, there's your added heat, and then that causes the pistons to start to move, and in the end, your car is going to be doing work. It drives you to school. Okay, so heat engine, refrigerator, those are the two main processes I want you to know, and it's all dependent on how we move around our cycle.